Hello, and thanks for using TickBoom, a free service that helps high school students with their math problems. I've had a student send through this question, which is a proof by induction question. So the result we're being asked to prove is that the sum from k is equal to n to 2n of k times k plus 1 equals n times n plus 1 times 7n plus 5, all divided by 3. And as we'll see when I work through this, the particular technique I use to solve this induction question, it's quite a handy one to have in your toolkit. It kind of is quite a common technique that you may find helpful when dealing with induction proofs that involve a summation. So it's quite a good one for us to work through. So I'll start by just writing out what we're being asked to prove. So we want to prove that the sum from k is equal to n up to 2n of k times k plus 1, we want to prove that that is equal to n times n plus 1 times 7n plus 5, all divided by 3. So I'll just start by working through the motions of induction. So for step 1, we want to show that this is true for n is equal to 1. So let's start by looking at the left hand side. So that's going to be the sum from k is equal to 1, n is equal to 1. So from k is equal to 1 up to 2 of k times k plus 1. So what's that going to be? So we're going to have k is equal to 1. So 1 times 1 plus 1 plus, and then k is equal to 2. So 2 times 2 plus 1. So that's going to be 1 times 2 plus 2 times 3. So that's 2 plus 6 is equal to 8. So that's the left hand side. Let's take a look at the right hand side. So that's going to be n is equal to 1. So 1 times 1 plus 1 times 7 times 1 plus 5, all divided by 3. So that is 1 times 2 times 7 plus 5 is 12, all divided by 3. 2 times 12 is 24, divided by 3 is equal to 8, which is equal to our left-hand side. So therefore we can say it's true for n is equal to 1. Now step 2 wants us, we need to assume that it's true. Now normally a very common kind of practice is to say assume true for n is equal to k. K just happens to be the arbitrary letter that we use. But that's probably not going to be helpful here because we've got k in our left hand side. So I'm just going to pick another letter. It really doesn't matter. I'm going to pick the letter M, just because there's no m anywhere here, so hopefully it won't cause any confusion. So I'm going to assume true for n is equal to some integer m. And what I really mean, or writing that out, what that means is that we're saying that the sum from k is equal to m up to 2m of k times k plus 1, that is equal to m times m plus 1 times 7m plus 5 on 3. So that's what we're assuming to be true. And that now leads us to step 3. So I'll just turn over. And for step 3, we want to show true for n is equal to m plus 1. So maybe what I'll do is I might start by seeing what the right hand side comes to when we insert m plus 1 for n, and then we'll do the same for the left hand side and see if that gets us to the right hand side. So let's start with the right hand side. The reason I think it's easier to start with the right hand side here is because it's a simpler thing to substitute n is equal to m plus 1, and then I suspect what's going to happen is we in expanding this summation, we're going to then make use of our assumption in step 2. So it's often easier just to kick things off in step 3 with the easier of the left and right hand side. So here we're going to, we'll have n is equal to m+1 times, and then we have n+1, so that's going to be m+1 times 7n+5, so 7n+1 plus 5, and that's all divided by 3. And what we need to do here, I think we'll just expand this and see what the expansion leads to. And then when we go through our left-hand side, we'll do the same thing. We'll just expand it and see if we get to the same place. So what I might do is, this is basically m+1 times m+2. So we'll get m+1 times m+2 times, and this will be 7m plus 7 plus 5, which is 7m plus 12. And then that's all divided by 3. And I might now expand this just 2 brackets at a time, so I'll start with these first 2. So we'll get m times m is m squared, plus m times 2 is 2m, plus 1 times m is m, plus 1 times 2 is 2, and that's all multiplied by 7m plus 12, all divided by 3. And now I'll expand the remaining brackets. So m squared times 7m will be 7m cubed. M squared times 12 will be plus 12m squared. 2n times 7m will be plus 14m squared. 2m times 12 will be plus 24m, plus 7m squared, plus 12m, and then 2 times 7m will be plus 14m, and then 2 times 12 will be plus 24, and that's all divided by 3. Alright, so now we need to just bring some of these terms together. There's only one m cubed, so we'll have 7m cubed. So with the m squareds, we've got 12 plus 14 will be 26, plus 7 will give us 33. So that's going to be 33m squared. Now with the m's, 24 plus 12 will be 26. 26 plus 14 will be 14 plus 24. Oops, no, 24 plus 12 will be 36. 36 plus 14 will be 46, 50. That sounds more like it. So plus 50m, and then just plus the 24 at the end. And that's all divided by 3. Hopefully I haven't made any arithmetic errors there, but I guess I'll find out soon enough when we get to the left-hand side. So there's not much more simplifying we can do there. No real benefit to dividing everything by 3, so let's just leave it like that. And now let's take a look at the left-hand side. Now the left-hand side will be this summation here. So we're going to have the sum from k is equal to, now instead of n, we'll have m plus 1, and up to 2n, or in other words, 2m plus 1 of k times k plus 1. Alright, now I'll just clean up this a little. So we'll have the sum from k is equal to m plus 1 to 2m plus 2 of k times k plus 1. And now at this point we will use the technique I mentioned at the beginning, the common technique that you might find can be used quite often when dealing with induction questions that involve a sum. And what we're going to do, particularly for this question, is we're going to try and link up what we've got here with what we assumed to be true in step 2, because we also assumed a summation in step 2, and that sum went from m to 2m. And here we've got m plus 1 to 2m plus 2. So what we can do is we can actually say, well, this summation here that we're dealing with is the sum from k is equal to m to 2m of k times k plus 1. And then we can make some adjustments because we actually want to start our summation from m plus 1. So if we're going to start from m, we have to subtract it so that we're effectively starting from m plus 1. Because in starting our summation from m, we've kind of added in m. So if we're going to add it in, we've got to subtract it. So we're going to then subtract the part of this summation where k is equal to m. So that would be m times m plus 1. Now the other thing is, if we only go up to 2m, then we're missing off 2m plus 1 and 2m plus 2, those two extra items, because in this summation we're going all the way to 2m plus 2. So here, the other adjustments we need will be to add on what the summation is at 2m plus 1. So if k is 2m plus 1, we'd have 2m plus 1 times 2m plus 1 plus 1, or 2m plus 2. And then we need to add on when k is equal to 2m plus 2. So we'll add on 2m plus 2 times 2m plus 2 plus 1, or 2m plus 3. So here these two lines are equivalent because whilst this summation doesn't include all the items, the total does, because we've made our adjustments here. And the reason why doing that is helpful for this proof is because we know what this is, or at least we've assumed what it is. What we did in step 2 is we assumed that this summation was equal to m plus 1, 7n plus 5 on 3. So now we can substitute that in. So we can say this is m plus 1, 7m plus 5, all divided by 3. And that's from step 2. And then we just have to keep everything else that we've adjusted for. So minus m plus 1, plus 2m plus 1, 2m plus 2, plus 2m plus 2, 2m plus 3. And now what we have to do is hope that in kind of expanding all this, do we end up here? Do we get the same thing? Because if so, then we've kind of done all the hard work. So I think the first thing to do is to get a common denominator of 3. So we've already got 3 here in the denominator, so I just need to multiply each of these by 3. So we'll get m plus 1, 7m plus 5 divided by 3, minus 3m, m plus 1 on 3, plus 3, 2m plus 1, 2m plus 2 on 3, plus 3, 2m plus 2, 2m plus 3 on 3. So now I can start the process of expanding, and then everything will just be on this common denominator of 3. It's kind of like what I did up here. I'll kind of do it a few brackets at a time. So here we'll have m squared plus m times 7m plus 5. And here we'll have minus 3m squared minus 3m. Here we'll have, I might just expand this 3 in first. So we'll have plus 6m plus 3, 2m plus 2. And I'll do the same thing here. So we'll have 6m plus 6, 2m plus 3. And that's all divided by 3. And I'll have to turn over at this point, and we'll continue with our expansion. So our left-hand side is equal to, and I'll have to do a bit of turning. So m squared times 7m will be 7m cubed. So we get 7m cubed. M squared times 5 will be plus 5m squared. M times 7m will be plus 7m squared. And then m times 5 will be plus 5m. And then minus 3m squared minus 3m. And then 6 times 2 will be 12m squared. 6 times 2 will be 12m. And then 3 times 2 will be plus 6m. And 3 times 2 will be plus 6. And then 6m times 2m will be plus 12m squared. 6 times 3 will be plus 18m. And then 6 times 2 plus 12m. And then 6 times 3 will be plus 18. All divided by 3. And now we need to just bring our like terms together. Again, there's only one m cubed, 7m cubed. Now I might just cross items off as I captured them, just so I don't miss anything. So I'll probably need my calculator here, just so I don't make a mistake. So in terms of m squared, we've got 5 plus 7 minus 3 plus 12 plus 12, and that looks like it, 33. So plus 33m squared. Now we'll do our m's. So 5 minus 3 plus 12 plus 6 plus 18 plus 12 plus 50. Okay, so that's plus 50m. Now just our final numbers. So we got 6 plus 18. So that's just our 24. So plus 24, all divided by 3. Now let's take a look. It looks pretty familiar. 7m cubed plus 33m squared plus 50m plus 24, all divided by 3. Beautiful. So that is equal to our right hand side. So therefore it's true for n is equal to m plus 1. So our final step, I'll just write by induction. Now you could write it all out in full if you wanted to, if that's kind of what you're expected to do. But I'm just going to write shorthand by induction. We can say the sum of k is equal, sum from k is equal to n to 2n of k times k plus 1 is equal to n plus 1, 7n plus 5, all divided by 3. And that's it. That's the induction proof done. I mean, you probably wouldn't guess that this is true just by looking at it. But that's the beauty of the induction technique. You can use this one technique to confirm what look like unintuitive results. I think the most interesting thing about this particular question was in this technique here, kind of jumping from the sum that we end up with when we're in step 3 with the n is equal to n plus 1, and the technique we've used to link it back to step 2 by kind of taking the original step 2 sum and then making our adjustments to get them to be equivalent. I think that's a simple technique, but It's rarely common that it can be helpful when you're dealing with induction proofs with sums. So if you haven't seen that technique before, definitely worth adding to your toolkit. It definitely will come in handy with these kinds of questions. So hopefully that all made sense. If you found that explanation helpful, please be sure to give it a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions that other students are struggling with, please be sure to subscribe to my channel so that you can stay in the loop. All right, tick boom.